Well, let me introduce the speaker, who we are very, very lucky to get Tom Muxlow. He has an extraordinarily busy programme, as I'll explain in a minute. He's driven all the way down from Manchester to be with us for tonight's lecture, and will be travelling all the way back to Manchester. So we've taken out a great deal of Tom's time today, and we're all very appreciative of that. Well, let me just give a brief intro to embarrass Tom. First of all, he studied physics at Imperial College before moving to the University of Manchester Jodrell Bank Observatory for his doctoral research on radio structures of faint radio sources. And his team at that time, he was part of the team, was developing the original Merlin imaging array. So very, very early days, wouldn't it? That would have been, Dick, when we worked in very early days. And this developed into the Merlin Very Long Baseline Interferometry National Facility. He is currently the principal investigator for the eMERGE Consortium project, and recently he's taken on a new role as the manager of the support centre for UK programmes on the Atacama Large Millimetre Submillimetre Array, which is the leading millimetre interferometer on the planet. It has 66 antennas in the Atacama Desert. I don't know if we'll hear about that, will we? Atacama.
That's at the end of our postscript.
Next lecture then. And make a note, Mr. Secretary. So 66 antennas in the Atacama Desert of northern Chile at an altitude of 5,000 metres. And the support facility for this is based at the Jodrell Bank Centre in Manchester. Anyway, I've cut the bio down, we've done lots of interesting things, but please join with me in welcoming Dr. Muxlow down to see us today.
Well, as been said, I essentially have been involved with the building and the running and the exploitation of Merlin for many years. I don't quite know if I want to say how many, but rather too many in some senses. But that said, there is a local interest here that I wanted to just introduce you to. Of course, Pershore, not quite close to the Birmingham to Bristol railway line. And they used to, I'll come to that, there used to be two telescopes there, both 25 metres in size. There is the one left, used by Jodrell Bank for part of the imaging array with the Merlin. I'll come to that in a while. I want to introduce you to this long-term project called eMERGE. It's the eMerlin Galaxy Evolution Survey, and in essence this is using eMerlin plus the VLA in the United States, which is one of the standard instruments for imaging in the centimetre and sub-centimetre wave bands, and that we have joined those together with a combination. I'll explain what that means. That means we're getting extra angular resolution, and the idea is that we are looking not just like everybody else in the sky, doing huge numbers of surveys. The EMU survey from Australia has just detected over 2 million sources, faint sources, but of course they're all points as far as they're concerned. So what we have is the advantage of resolution over a reasonably large area of sky to actually investigate these in detail and see what they look like, because of various things that can give rise to radio emission, one of which is star formation, active galactic nuclei. And through the history of time, both of these have evolved in similar ways, and we want to see the details of how they are interacting in the distant universe. So that's what this is basically about. We are only part of the way through. Data were taken on eMerlin back in years old now, 7 years old, some of it. When we took it, we realized that we did not have the computing facilities or the expertise and sophisticated software to deal with the problems that was going to incur in trying to process the data fully over a very large field of view. unaveraged, we're talking about 30 terabytes of data. And we're talking about many millions of pixels and large Fourier transforms back and forth from data to the sky. I'll come to that in a bit. So anyway, DEFRD is part of eMerlin. In the early days when I first came to Jodrell, I inherited some data from DEFRD. I'll come to that in a second. But DEFRD is an important aspect still in eMerlin. So when you go past on the train, or you can see it as you're driving close by, remember, it may look like an ancient old telescope plugging away, but it's a part of a significant astronomical instrument which is open to, well oversubscribed by astronomers across the world and continues to be so. And it's just one of 6 or 7 telescopes across England. I'll come to that. Anyway, so telescopes across England. I'll come to that. Anyway, so let's get started. Let's see what happens if I can advance the slide. So, where is Goods North, the actual field? Goods North is the optical deep field from the Hubble Space Telescope, and it's the favoured northern sky window. It's up near Ursa Major here. It's only about 20 of the size of the full moon, which is about 30 arc minutes. So it's a tiny patch on the sky, but that took an awful lot of observing with the Hubble Space Telescope. I'll come to that in a minute. For comparison purposes, as I say, I put up the full moon there. Of course, the moon never gets this high in the northern sky to be anywhere near this constellation, but that's therefore. Also in this region, there's been a huge campaign from not only the Hubble Space Telescope, but X-ray satellites looking at these galaxies, infrared with Spitzer, far infrared with the Herschel Space Observatory, and a lot of ground and optical UV with Kitt Peak, Subaru, and many others. These, of course, at lower resolution, but with amazing sensitivity, because these have got huge mirrors. The Hubble Space Telescope is a 2.4 meter mirror, which by modern standards is relatively small, but has the advantage that it's above the atmosphere. And of course, in the radio, eMerlin, VLA, and also, as I'll show, VLBI at 11,000 kilometers. Okay. What is the eMerge radio field? Well, the initial part of this is the initial 15 arc minutes in the middle. This is the patch on the sky that the Lovell telescope, which is part of the eMerlin array, when it's needed for sensitivity. There are 6 basic imaging telescopes across Britain for eMerlin. But there is a 7th, a large one, at Jodrell Bank itself. That is also added into the array. It doubles the actual collecting area of eMerlin, simply from the area of the dishes, and therefore increase the sensitivity, make a contribution to the quality of the image, apart from improving the signal to noise in the data. But it's important when you're pushing to the faintest objects we can see in the sky, and to image them in detail. Whoops. That are present in that the central part in the 15 arc minutes has been processed. These data have been averaged because they don't need to go right the way out to the edges of the primary beams for the smaller 25 meter antennas we have around Britain. But the 25 meter antennas we have around Britain, but the Lovell can only observe the central part, and beyond that it's outside the primary beam. But that said, bear in mind that radio telescopes, unless they have phased array feeds, which none of ours do, because we don't have room there to really do anything significant, they are all single pixel cameras, okay? But when you join them together and you map out the whole of the primary beam of the Lovell telescope, it goes from a single pixel to 81 million pixels. So you can image the whole of that field at the full resolution of an aperture out that field at the full resolution of an aperture out across England. DR2 is now being processed. We used DR1 as a pathfinder to check that things were working properly, and we dealt with DR2, which is a much larger data set, much more complicated with regard to mixing of telescopes of very different sizes. And also, of course, we have VLA antennas added in with these data as well to add short spacings. So, say, the inner 15 arc-minute field, 25% of the Merlin data, plus all of our 42 hours of VLA 20 centimetre data, and also some C-band data at 5 centimetres on the inner part of it as well. That is now all released to the consortium, and we're doing some analysis of those sources. The central part of here is at a sensitivity. I'll come to show you what that means, but it's 1 microjansky per beam, and we're looking to go ultimately in DR2 down to 500 nanojanskys here, plus an annulus of 1 microjansky out here. And of course, we've worked out how we're going to smoothly move from the central part to the outer part without having to make a break. And it's all in the imaging and into another. And also bear in mind that these are all data sets with very large fractional bandwidths. So there's at 1.5 gigs L-band, we have 500 megahertz of bandwidth, so that's a 33% spread, which means that the beams at one end are significantly different from the size of the beams at the other end. But we'll come to that. Okay. Right. So how this talk is going to, and point spread functions. I should perhaps hold this. That's better. And point spread functions. And then I'm going to talk about imaging with radio telescopes and how we do that, and then actually come to windows on deep time and show you a very simple model of the universe to explain why we see what we see. For those of you who perhaps don't quite appreciate how amazing it is to look out at the universe. But I find it really fascinating. I feel really lucky to have spent my life doing that. It's a privilege. And then we look at the eMERGE survey and some of the results I've had. It's a privilege. And then we look at the eMERGE survey and some of the results I've had, and then some concluding remarks at the end. So let me learn which release I have to do. This one. Okay. So Defford, this is called Galaxies. Defford is close to Worcester, and our telescopes are always able to look at this field because it's higher for the northern sky. So this little patch of sky near Ursa Major is always above the horizon, above Defford and our other antennas. The interferometer was put together by Dr. Hay, who built the Defford radio interferometer in 1962, and he did some very useful radio astronomy, looking at radio emission from solar flares, radio echoes from meteor trails, and in fact identified the position of the first powerful extragalactic radio source, Cygnus A. The size of the telescope aperture, by essentially moving these two telescopes apart out to about 1 kilometre, north, south and east, west, increased the angular resolution, and they were able then to separate different components of sources if they could, or certainly improve the measured positions of these sources. Through to the end of the 70s, the collaboration with JBO, as I've said, Jodrell Bank Observatory, one of the Defford telescopes used to do regular single baseline interferometry with the 76-metre Mark 1A. The data used to come back via a microwave link, return link, and it's important, of course, that across the aperture you have to maintain coherence, that all the phases and all the electronics are locked up to the hydrogen maser clock back at Jodrell, and the coherence is maintained by a forward and return L-band link over the radio, same radio, and return L-band link over the radio, same radio links from microwave tower to microwave tower, all the way out to the outstation, and then back again, of course, with the actual data. And that was quite a first, to have a picture that big that was phase stable. So with 127 kilometres of separation, source positions and sizes to better than 1 arc second could easily be found. And as I say, when I came to Jodrell, I was given this PhD project with a large number of paper tapes, if you remember those, that dates how long ago this is. For 408 megahertz low frequency data on the Deford Mark 1 interferometer, basically to characterize the radio source structures against the flux densities. Of course, the single baseline data, it showed how much we saw or detected of each source we looked at, showed you the percentage of the emission, because we knew how much the total emission of each of these catalogue radio sources were, then we looked at them and we saw how much we saw of that, which is not usually not 100%. The single baseline data shows of angular size up to or less than 1 arc second. Now, most of these objects are the vast majority of that were these double-lobed radio galaxies, where there's a supermassive black hole in the centre of an elliptical galaxy, which is accreting material. The accretion disk gets very hot in this inner part, and it's spinning very rapidly, and plasma off the accretion disk gets scooped up by the rotating magnetic fields, focused, accelerated, and sent out in jets. Magnetic fields, focused, accelerated, and sent out in jets at right angles to the accretion disk. And these jets punch their way out into galactic space. Sometimes the jets fall apart. Other times they stay tightly wound as hose pipes of plasma moving close to the speed of light, and they go all the way out to terminal shocks, working surfaces in hotspots at the end. But these all have compact features, cores, compact hotspots, and as you get further away, they get smaller, and therefore they increase because this whole structure gets smaller. So basically, as we come down from strong to medium to faint sources, you see here we're moving out into distant space, and the object's getting smaller. But then, as we got down to the faint radio population here, it went the other way, and nobody understood that because models you have of the universe where this stops going on forever. It turns over a bit, but it doesn't come down again significantly. So we didn't know what this new source population was, and that was going to be one of the main projects that I was going to pick up after I did my thesis. That said, we got diverted into making our E-Merlin array and making a proper imaging telescope that actually could image the whole radio source and tell you what the real structure is, never mind just what compact bits there are within it. Okay. Now, I want to talk about apertures, angular resolution and point spread functions. I'm sure many of you know quite a lot about this, but for those of you who don't, I just want to run through this quite quickly to point out that this, with an optical telescope, tells you why you do things with telescopes of certain sizes, and is relevant for the radio because we try to get the same resolution in radio at much longer wavelengths with optical light. So I'll come around here for a second so I can see. I might be way there. A fully filled aperture like this. Diffraction of the refraction, basically the diameter across the aperture itself, the front lens, and in essence, if it's stable, then light goes into this, and light from any point on the aperture, with light close by it joining, and then connecting at the far end again to make the image. Those light beams that are very not separated very far at all, in fact next to each other, if you like to think of it that way, they're telling you about slow variations in the brightness of the image. As you go aperture, provided the aperture is, as I say, is coherent and there's no jiggling about of the arrival times, then as they come together, they're looking at higher changes in more sharper changes in the brightness from dark to light and back again. And at the edges, then there's only the edges across the aperture to give you the very highest resolution on the image. Now, what we're talking about here is these are what the elements of this are spatial frequencies. Now we know what frequencies. Now we know what frequencies are when we can't think about things like hi-fi, right, or music. Here is hi-fi, maybe, and this has both bass unit and treble. And if you were to bass unit and treble, and if you were to analyze the frequency content of a short burst of music, you're doing what we call is a Fourier transform to invert the information. It's the same information but in a different form. So if you take a burst of music, Fourier transform it, it goes from time, and that's hertz, that's frequencies, okay, cycles per second. So bass is low frequencies, treble is very high frequencies. And for pictures, if you imagine this being now a picture, a black and white picture, if you just filtered out all the high spatial frequencies in this direction and in that direction, and if you only had low spatial frequencies present, you would notice that this was lighter, there was something here, and this was a dark patch, but you wouldn't see any detail. So if you want to see more detail, you need more and more treble, in effect, in spatial frequencies. Okay? Or, in effect, in spatial frequencies. Okay? So if you look here, this now is what's called the modulation transfer function, but it's really the weighted spatial frequency sampling of this aperture. So this aperture is really good at getting low spatial frequencies, because for low spatial frequencies, everything is close by its neighbour. But as you get to larger separations, there's less and less of the area that you can use until you get to this point here, where it essentially drops to zero at the edge. Okay. Now that's like half a triangle. So that's basically, it's the weighted spatial frequency sampling. So that's basically, it's the weighted spatial frequency sampling. So these spatial frequencies are well sampled and these less so. But the weighting means that these are far more measurements from here than there are from here. So you take that shape here and reflect it around zero, you perform a Fourier transform, which is a central peak and these ripples around the edge. And of course this is in 2 dimensions on here. And this in fact is, if you were to look very carefully at a bright star in this perfect optics, it's still not a point, it's this airy disk, okay, with the little rings around it. As this gets bigger, the aperture gets bigger, and it stays coherent, then of course this moves out, and if this moves out, then this moves in. So that's telling you this is what a point looks like, but if you get a larger aperture that's coherent, then point will look more point-like, because this will move in. Okay, that's adding resolution. So that's what happens with small telescopes like that. I have one small telescopes like that. I have one like this, an 8-inch aperture, which works pretty well when the atmosphere is okay. I used to run this observing sessions in my back garden in Middlewich when I lived there. The problem is that I'm surrounded by houses, and you do discover heat escaping through people's roofs. Does, because it heats the air above the roof, and it destroys the coherence of any image that you're looking in that direction close above the roof. Anyway, so provided the basically with a 200mm aperture and a 550nm wavelength, which is green light, the equation says 1.22 lambda over d in radians gives you what the size of the image is going to be. And that, if it's working perfectly, comes out at about 1.4 arc seconds. Of course, if it's not that stable, you're going to end up with differential delays across the aperture, which means that it appears that the wavefront is tilting one way or the other way, and it just basically blurs out the image if it's bad seeing. But on a perfect night with good stable atmosphere and the actual temperature of the air in the telescope being the same as the air outside the telescope, which also makes a problem, but can do. But then you can get very good images. Of course, if you want to go to a professional mirror like Gemini North, that's 8.1 meters. The mirror is 1,600 times the collecting area of this little guy. So it's really, really sensitive, of course, which is what we want. But unfortunately, it's not fully coherent. If you look at the total atmospheric seeing above the telescope that they publish, you'll see that can be some very bad nights and some very good ones too, but the mean here is 0.7 of an arc second, okay, which through the atmosphere is about twice the diameter of my aperture here on that telescope. So that's 0.4 of a meter. So you're getting 1,600 times collecting area, but you're getting only 400 coherent patches. So basically, each one of those patches limits your resolution, and you just stack them up on top of each other in the telescope. That's logically what's happening, and they're incoherent with each other. If you really want to get the full resolution of your telescope, you really need to go. And it's a large mirror. You need to go above the atmosphere, which is what the Hubble Space Telescope and now the James Webb are doing, of course. Okay. In terms of apertures and the radio, of course, the radio is much longer wavelength, and therefore, to get the same level of detail on an object in the radio, you're going to need a much larger aperture. Okay. So, in order to get a workable image in the radio at about 0.7 arc second resolution in its centimetric wavelengths, the VLA here in New Mexico has 27 dishes, actually has 28. One's cycled round in engineering at a time, and when it's fixed, it goes out and another one comes back in. But 27 operational ones along three railway tracks and posts with a machine that picks the telescope, takes it along, puts it down somewhere else, and basically they're through to 35 kilometers. Okay, and this is a beautiful fit to sorts of resolution that you routinely get from large ground-based optical telescopes. Okay. Again, the synthesized radio aperture is made coherent by locking all the receiver LOs to a laser clock and by correcting for geometric and electronic delays between telescopes. Of course, as you bring the data back from each dish, you have to then combine them together in a correlator, and when you do that, you know where you are looking in the sky, you know what the time is, you know what the Earth is doing, the sky, you know what the time is, you know what the Earth is doing, you know where your telescope is, and therefore you can work out the geometrical correction that you have to put in for the delay between each of the telescopes to bring it back to being coherent. Okay? But beyond that, there is an additional delay caused by the column above each telescope, especially if they're far apart, where there's a difference in delay in the atmospheric column of each telescope, and it changes on time scales of about a few minutes. Okay? So you have to, you stop looking at your target, you go to a known object at a known position, which is a good point source, and you measure when the radio waves arrive. You go back on your target. You do it again. Go back for 90 seconds, back on your target. 90 seconds, back on your target. And you solve for the delay above each by called phase referencing on this nearby point. That allows you then to take the array, calibrate the data, and Fourier transform your weighted spatial frequency measurements into an image. Measurements into an image. And here is a beautiful radio image taken by the VLA with a number of configurations. And this is the radio galaxy 3C348. This is one of these galaxies that has the double lobes, but the jets begin to fall apart quite quickly. And you can see that there's an accreting supermassive black hole here, active galactic nucleus, relativistic jets coming out and plasma in those jets, and lobes where they end up. Okay, and you can see that the feeding of the AGN is intermittent, and these jets that restart and new blobs come out.
Well, that's an amazing detail.
It is a beautiful radio photograph. Yeah. And then, of course, you can add the visible sky under it. And there is the host elliptical galaxy, and this is the radio image coming from it. So, as I say, this is a distance of 2 gigalight years, 2 billion years, so life hadn't quite got going on the Earth at that stage yet, but the solar system is about 4.5 gigalight. And the linear size of this, from side to side, is 1.5 million light years. E. Merlin is, with its aperture now of 220 kilometres all the way to Cambridge. Okay, this extends the aperture, and now we have routine imaging at centimetre wavelengths, which matches the Hubble Space Telescope. Okay, space telescopes, whereas we are a match for the HST. Saying is that, say, 5 centimetres at 220 kilometres aperture is the same as 2.4 metres. Well, it's the other way around. One of these should be 220 kilometres over 5 centimetres is the same as 5.45 times 10 to the minus 7 metres, which is green light, over 2.4 metres mirror for the Hubble Space Telescope. So it's the same number of wavelengths across the aperture, basically. So this is, in fact, a combination E. Merlin plus VLA image. E. Merlin, of course, the shortest spacing we have is about 10 kilometres, and that cuts off some of the low ends of the spatial frequencies it samples. So we add those in by adding in VLA, and we sit over and beyond the VLA. So this is a combination image. The central kiloparsec in the nuclear region of the nearby starburst M82, which is about 12 million light years away, so it's quite close. This is M82, it looks a bit desperate. Basically, M82 is crashing into M81, or the region around M81, at about 200 kilometres per second. And this interaction is actually triggering massive amounts of star formation, but only right down here in the nucleus of the galaxy. And what happens is that the supernovae generated by that star formation, when you make stars, you make mostly low mass stars, and then quite a lot of, but not that many, medium mass stars, and some rare high mass stars. But the high mass stars dominate things because they're so bright. And basically, the lowest mass stars, when they've been made, the universe hasn't actually existed long enough for any of those to die. Okay, that's not actually true for the Sun, which is a medium mass star, medium-ish. It's going to be here for another 4.5–5 billion years. But the high mass stars, we're talking above 8 solar masses, 20, 50 solar masses, they go through their lives, they live fast and they die young. Right? They actually live for about 1 million or 2 years. That, in astronomical terms, that's a very, very short life. And anything above 8 solar masses, when it dies in a huge supernova explosion. And these high mass stars have spent their time burning hydrogen to helium, helium to carbon, all the rest of it, and they are generating all the higher order elements within the star. And when up to iron. which is the most stable element. And when the whole thing collapses down and then blows itself up, all of that gets sent out, and it's from that all the planets are then made, because primordial material from the universe, the beginning of the universe, doesn't contain any of that. It's all made in stars. But the plasma from those explosions, and we see these supernovae going off.
Tom, that little arrow is the air mouse on there. If you've got to press another button.
Yeah, I know, I'm aware of that.
The laser point.
There you go. Oh. There. Tell you what. I'll just press this, move it from there. Okay, and I've still done the wrong thing. Okay, we should move on. Basically, so all of this is coming from supernovae that have gone off, and we see a new supernova going off. We don't see it in the optical because there's so much gas and dust in here, it's completely obscured. You only see it in the radio sees right through dust. And we can actually see these coming and going, and we get one going off about every 5 to 10 years. In terms of the fidelity of this image, it's really quite good. In the early days, we effectively had monochrome systems. We just observed at one frequency with a very small bandwidth. But now we are utilizing huge bandwidths, and of course each of these lines, this is the combination, the projection from the source of the separation between all our telescopes over 24 hours as they go around each other. Okay? And that is the aperture being sampled out to these spatial frequencies. But if you have large bandwidth and a large fractional bandwidth, each of these lines spreads out by the relative bandwidth of the data, and it fills itself in like this, and you can fill in the center bit in here with the VLA. So that's what we do here. This is a multi-frequency synthesis, which is what this is, 5.5 to 6.5 gigahertz with the VLA, and that's with 100 milliarc second resolution, and you can see all these relatively young supernovae. These compact objects here are all less than 100 years old, but as I say, ones appear quite regularly, and if you then just look at the Merlin data, you filter out all the extended stuff that the VLA is telling you about. So if we separate that, then we can actually see these individual supernova remnants. And this is this one here, there, and you can actually measure their size and see the sizes getting bigger as it expands. This is down to 16 milliarc seconds resolution here now, which is higher even than the HST can get to. Now, it's not clear exactly what the slowdown rate is on this one, but in essence, this must have got up. We didn't see it when it went off originally. We didn't have telescopes to actually pick it up at that time, but this went off apparently in about 1970, or between 1960 and probably 1980 is the latest. But we started, I suspect it's around 1970 when it went off. That is an expansion velocity of around 11,000 kilometers per second, which is a sort of going rate for the stuff coming out from supernova explosions. So, I've just gone through the basic types of radio source that we have. And these are double-lobed radio sources, creating supermassive black hole AGNs, extended plasma jets and extended lobes, and also star-forming galaxies, relativistic plasma ejected from exploding supernovae. There is another category here called, this is a radio-loud AGN, basically, as I say. These are accreting AGNs, accreting supermassive black holes, 10 to the 8 solar masses and more, and the jets are collimated and accelerated, and these punch their way out of the host galaxy. Radio-quiet AGN do have an accretion and an active nucleus and produce jets, but these jets are not particularly powerful for reasons that we're yet trying to find out, and that's one of the reasons why we're looking at some of these objects in the early universe to see what they're like. They don't escape the host galaxy. And then we have the star-forming galaxies, which are basically like super M82s. So as I say, here, this comes from supernova remnants from the high mass stars that have just been made and then explode. So, I'll learn about this at the end of this. I think I'll keep pressing the wrong one. Anyway, so the Goods North Field, so it's a window on deep time, and last of my little asides to come about this model of the universe to show you what I mean before I give you results from DR1 and show you some of the actual results from our survey. The first part of it, of course, the main part is due out in 2023. This is an integration by this telescope of 46 days, 3.6 million seconds. The DR1 area is 1/660,000th of the total sky area. It's a tiny little patch. And it contains, within the DR1 area of 15 by 15.5 minutes, 13,030 galaxies with magnitudes brighter than 28.3 out to redshift. The most distant object they've come across is something, the fragment out at redshift 11. So, what I want to tell you about is that the astronomers have the unique ability, and it's a real privilege, to observe history directly. Because wherever we look out there, we look into history. And how is that possible? Well, it's very difficult to sort of see that with the three-dimensional universe that we have, plus time. So, I want to just consider a simple model for the universe. The universe has three spatial dimensions folded in time. That's difficult to make an easy model of because we only have three spatial dimensions to play with. So let's simplify it by collapsing the universe to two spatial dimensions. That's a graph paper universe. And it's populated, whatever lives in that universe is populated with concept of length and breadth, but no height. So flat ants or whatever it is, they're flat galaxies as well, you know. But they're basically, it's a simple model. The universe exists on graph paper or a thin sheet. Okay. Imagine spreading the graph paper out over the surface of the sphere like this. Of course, it's a two-spatial dimensional and finite universe because at all times the surface area of that balloon is finite. If you start with zero size and then inflate it, the universe grows in size, but is always finite. As each second passes, it gets bigger. So the universe gets bigger and bigger, but it's always finite. So this is a two-spatial dimensional, finite expanding universe. And I'll try to make a model to give you some idea. So here we go. Getting bigger and bigger till we get to here, where we are now, 13.7 billion years after the start. So we're here and now. And what is happening with this universe is that as it expands, the fabric of the universe and the fabric of space is stretching. The graph paper is rubberized, it's stretching. Okay. Beyond the local motions where galaxies are in orbit around each other, if you look away, you notice that everything is moving away from us, and in fact everything is moving away from everything else, because as the structure expands, galaxies move apart. Okay. And when we look into the universe, we see that everything is moving away from us. But that's true for every observer in the universe. It's not unique. Okay? More distant flat galaxies, I say, are moving away from us more quickly. However, things are a little more complicated than that, and that is because information, radio waves, infrared, light, ultraviolet, X-rays, gamma rays, gravitons, all travel at 300,000 kilometers per second, c. The further out we look, the longer the information has taken to reach us. We are here and now, but we can only see there and then, not there and now. So we're here, we can't see that point. visible, truly that the universe is finite, and this is the size at 13.7 billion years after the Big Bang. The position where the Big Bang happened is no longer in this universe. But the visible universe is different to this. We don't have the luxury of seeing the whole universe at one instant of time. So the visible universe is shown here. As you look out, you look back in time, okay, to when the universe was smaller. The visible universe in this model is the surface of a teardrop going back in time to the very start of the universe. And now the shape of this teardrop is not quite right, but I only could find certain shapes of teardrops on the internet. So, but in essence, this is basically like a balloon, if you like, with water in it. You're holding up. It's thin at one end. As you go further back, you're seeing the universe as it was at an earlier age. Okay. There is there and now, but what we see is there and then. And that's true. And the most distant thing you can see is the beginning of the universe. You can see now that basically inside this is past time and outside this is future time. So this universe is expanding into time, as is our universe. But it's rather more difficult to imagine how 3 dimensions expands into time, but this shows how 2 dimensions goes into time. So, anyway, the most distant thing you see beyond all the galaxies is the afterglow of the Big Bang. This vision, by the way, is what every observer sees. You can move this over to here, and the observer thinks that they are the most developed part of the whole universe and everything else is history. And they will see our galaxy as it was many, many billions of years ago. But that's true for every single observer. And if you look out along the skin of this visible universe, if you look in different directions, you go through different individual galaxies, flat galaxies, but the same sequence of history brings you back to the start. Whichever way you look, you come back to the start, but from a different direction. Just as you look in the sky from us, if you look out through a patch of sky, you look through history back to the start. And if I look in this direction, you look through history back to the start. It's a different set of galaxies you're going through, but it's the same history. So we actually do see history. We don't have to work out what history is, we see it. So that's a great privilege. And the most distant thing you can see is the afterglow. This is the actual picture from an all-sky image of the cosmic microwave background, which is the afterglow of the Big Bang. Okay? From the Planck all-sky image from the Planck satellite, the last scattering surface of the fireball, when it reached about 3,000 degrees, as it expanded in the early universe, it was very, very hot, obviously, in the first few seconds. But as it expanded, it cooled, and it got to about 3,000 degrees, and at that point, atoms formed. The electrons and the protons were in free motion, and they recombined, and it became transparent to its own thermal radiation. So that is when that's the last thing we can see. So it was when it was about 3,000 Kelvin, which is like orange light, and that's about 380,000 years after the Big Bang. It had a redshift of about 1,000, so it's a long way back. And what we see is very accurately a thermal spectrum, but instead of being 3,000 Kelvin, it's 2.72548 Kelvin with that error. Okay, and that peaks in the microwaves, 1.9 millimeters. So here we look at the sky, and you can see the fluctuations in here. This is minus 300 and plus 300 microkelvin on this. And these hotter points in here are regions of higher density, and it's those hotter points that went on to start to create the galaxies, and the huge clusters and superclusters of galaxies and strings of galaxies separated by voids where it's cooler. But I'm looking at stuff way, way after that. Okay, I have a professor in a department in Manchester who is a cosmologist and works with this, and he complains that what I'm doing is just looking at boring foregrounds that he has to subtract out to get at the really important stuff. So, we have the eMERGE Deep High Resolution Radio Survey of Goods North, the HST ACS Advanced Camera for Surveys. Images are aligned with the combination radio images to better than 10 milliarc seconds, so we know exactly how to translate the optical against the radio. The wide field imaging overlays the ACS field with sub-microjansky sensitivity and sub-arc second angular resolution imaging to right the way down to milliarc second scales. DR1 release, initial verification of the central inner 15 arc minutes has been released to the whole consortium. There's about 150. How do I stop that?
Press escape.
Escape.
That's it.
Okay, thank you. And there's about 90 or 100 people in that consortium, and they're working on those data. But of course, the full data is what we want, because that goes down by a factor of 2 in sensitivity in the inner 15 arc minutes, and goes down with another 3 times the area, down to 1 microarc second in the annulus around it from the 25-meter antenna that we have in the eMERGE. That's due to come out. That's due to come out in 2023. And when I talk about redshift, by the way, what is it? Well, basically at low redshifts, it's V over C, the ratio of the velocity of recession against C, but in truth, as you go to higher redshifts, you have to take care of all the relativistic effects, so it's basically this. Z is the square root, redshift is the square root of C plus V over C minus V minus 1. But this all works up to about a redshift of 0.3 or 0.4. They're essentially the same, but they deviate beyond that point as the recession velocities become relativistic. So, what is it that I'm looking at? I'm looking at the microwave radio source population, and if you look at the source counts, here we're talking about flux density of objects. These are bright sources. Thousands, that's above a Jansky, coming down to a millijansky, and they're down to a microjansky. These sources here, this is a differential source count, so this is the difference between what we see from what would you expect if there was no change to the density of radio sources around us and we just kept on increasing the volume, okay, by stepping out with the volume. But what it shows is that in fact there is a big bulge of radio sources that appear at a greater distance, and these are the classical double radio loud AGN, and as we go to the fainter and fainter sources, we actually run out of those. We can see all of those to the edge of the universe. And what we see now here is a new distant star-forming galaxies, which is what we really want to investigate, along with less active AGNs. And this, in fact, this bump here was what I was actually seeing all those decades ago with the Defer Marconi interferometer. No, I didn't realise that, but I'm coming back to revisit it in my dotage, as they say. So basically, as you come down here, the content, the AGNs in here, the radio loud AGNs disappear almost completely. Star-forming galaxies become dominant, and in here there's also the radio quiet AGN, which begin to become more dominant. To the radio loud ones just disappear because we've run out of them. They're so powerful that we see them right the way through to the times when there were no galaxies. So We are interested in these, the radio quiet AGN, and also the star-forming galaxies.
When you had that first data point during your PhD, you've now got many data points, and you said you didn't understand why it went down. But now you've got some curves. Are these theoretical predictions?
No. Well, these are, but these are the real numbers that we have sources that we measure.
The lines, the lines going through the data points.
They're fitted, but there is some difference in here from the different deep fields. There's different selection effects in them, but these statistics now, we're getting millions of sources down in here now. And
I just wonder whether those were models of, if they were physical models rather than fits to the data.
Well, yes, some of these are predictions of starburst galaxies with certain radio to infrared characteristics with a Q, what would be 2.5, but these are how they actually contribute to that. And this is the AGN, the big powerful AGN that just disappear, and over this region here, then these become the dominant ones. These are higher density in the sky, and these just disappear. So microjansky sources contain virtually no classical radio loud AGN. They contain radio quiet AGN and star-forming galaxies, and that's what we're looking at with the eMERGE survey. I think I've talked to you about this. This is basically DR1. This is the central part of our study. 15 arc minutes across, and this is the DR1 release. 848 radio sources are catalogued in this central part of this field, and this is just the first study. The second part will include the outer part in here. This will go down a factor of 2 in sensitivity, and the rest of the outside here will be the same sensitivity as this is. So we will get 4 times the area and twice the depth of this, and complete new sampling of these for the DR2. I won't go into all the details here, but basically we have lots of new data. These now completely enclose all the HST candles field, so that now we're getting far more coverage of the HST images themselves with the DR2, and we predict that we should be able to detect more than 4,200 radio sources in this DR2 field. And that's a lot of sources to study in detail. Okay. So here is the VLA image of the sky at this point. VLA only, lower resolution, about 1.5 to 2 arc seconds beam size. Still, they've got their little ripples around them, you note. So even with all our apertures, we still get airy disks as well because of our sampling, and that's what these are. But we have the advantage that the airy disks from this image are easily definable mathematically and are consistent effectively across the whole image. So we are able to deconvolve them from the basic raw image. We do that by we can construct the point spread function. It's very easily done. You take your data, which has amplitudes and phases, and you put a 1 in all the amplitudes and a 0 in all the phases and Fourier transform it. And that gives you the point spread function. So what you do is you take the central part of the point spread function and you center it under one of these, one of the bright things, and you subtract away perhaps 10% of it. And then you search around and look for another one, the next brightest one. Subtract 10% of that, and you subtract flux from a number of these positions, and you're subtracting out the actual point spread function as you do it. Okay? And then at a certain point you stop and you take the list of those sources you've subtracted, go back to the data, subtract them out of the data, and remake the image. Then you start again. So this is called cleaning. You can end up with, to clean a large field like this where you've got 45,000 pixels on the side with many terabytes of data, it's going to take you a long time, a lot of computing effort, and that's what we've been checking that we can actually do, because we couldn't do that when we first got the DR2 with the full data. We've been waiting to actually get our ability to make these images. So that you can end up with something like 500,000 iterations, transforming the data back and forth to between data and sky. In here is the initial DR1 image of this central part here, and you see there are two sources here, this one and this one, which are problematical because our data were taken over about 3 years, and we have different observing sessions, and we get a few weeks of observing, and then we get it goes to somebody else, or a few days out of those weeks observing. We get another 4 or 5 days observing in a year after that. And these sources actually vary. They're bright points. They are little AGN cores, and they vary. And we've had to account for the variability because the noise map in here didn't do that, so we've managed to clean that up. But you do notice that the level beam here, okay, at the edges here, the actual noise level rises because we're getting out close to the edge of the primary beam. But this is the central region here where the level primary beam mostly is, but here it's getting really quite noisy. But when we add in the outer part here, then we will be able to move from just this inner part to the outer part seamlessly and clean it. So anyway, that's the plan, and that's what we're doing. And when you clean, you see that all those airy disks go away. And there is part of that image. Here is one of the few DR double-lobed radio sources. There's only about 10 in the whole field, and there's thousands of other sources. This is a wide-angle tail. I'll show you about it in a bit if there's time. So this is part of the 848 images sources. We use the VLA to make the catalogue because it doesn't resolve them. You don't want to use a telescope that resolves them to count how many are there. You want them all to be points. And then you take eMerlin, add it to the data, and resolve them and see what they look like. And what we're really looking at here is the variability of star formation and black hole growth over time. And here is here and now, and we look back into this tiny window on time, and as you go back through redshift and look back time in gigayears, this is the rate at which black holes are being built in the centres of galaxies, and this is the rate at which stars are being made in the in galaxies. So it comes up and gets more and more active in the universe to about a redshift of 2, and that is high noon for star formation. It's also high noon for assembling large supermassive black holes. This is all done from X-ray work. Clearly, these do go together. Star formation and black hole growth go together. We don't quite know how yet. The issue is that star formation and black hole growth are co-evolving, closely linked, but AGN can trigger as well as quench star formation. If an AGN bursts out with a huge amount of energy, it can clear the gas away from the central parts of the galaxy, and that stops stars forming. Alternatively, if it makes jets, those jets crash into things that cause shock waves, which then switch on star formation. So it's a complex thing. So we need to be able to resolve these systems and see if we can see embedded cores and jets within these galaxies. And the other thing is the star formation rate turnover at 2 down here is still problematic. All of this is constrained by ultraviolet traces. These are the very bright blue massive stars in those systems. Problem is you can't see any ultraviolet there because there's so much dust there that it's absorbed and it's re-radiated in the infrared. But there are so many correction terms to try and estimate what the true star formation rate is from the ultraviolet that this needs to be checked with something that is not that goes through dust and essentially it's transparent for dust. So that's radio. So we need to check this turnover here that it's at the right place, rather than some of these. Well, there may be some problems in interpreting the corrections due to the dust absorption. These are our catalogue 848 sources in DR1. You can see the distribution by redshift is that we're dominated by high redshift systems and mostly around redshift 1 to 2, and then a tail back here to redshift 6. So here's redshift along here, here's the luminosity of the object, here's the equivalent star formation rate. Star formation rate that luminosity implies if it's a star-forming galaxy. That doesn't mean anything if it's an AGN. AGN can have these luminosities, but we can tell which they are by their morphology. And you can see that this is the cutoff of the sensitivity of the DR1 release here. That will come down and more sources will be added to this. Okay. These are just some of the individual sources referenced in the paper that I wrote, giving a basic description of this. But there's nothing different about them except that they appeared in the paper individually, that's all. Okay. So high resolution Hubble Space Telescope images, I just love them. And here is our nearest neighbour galaxy, large barred spiral, and this is M31, distance of 2.5 million light years, 220,000 light years across. Milky Way is smaller than that, and Milky Way itself, which is a smaller galaxy, contains 100 billion stars. And all of these are the stars we're looking through to see this. The galaxies in emerge are much, much further away and much less impressive than that, but we can see them. Some DR1 examples. Right, I've just got a few of these just to show you what they're like, to give you a flavour. The real science comes with DR2, so maybe my successor will come and give you a talk on that. But here we start with the equivalence of M82s, okay? Classical star-forming galaxies, radio emission from central region. In this case, this is a 24 microjansky peak, so this, and the whole thing is 45 microjanskys of radio emission in here, and it's along the central part of this galaxy. In fact, you can see that the central part is actually obscured by dust. This background here is a false color image of the HST image, monochrome image in HST, but it's easier to, if you just stick with one color, don't try and show the real colors, it shows you the full extent of the galaxy, and that makes it easier. So this is in this position here, down sub 100 microjanskys, and this is the classical extended starburst, and there are many, many of those. Less than 100 microjanskys, the radio source population is dominated by these. Okay, so that gives you a star formation rate of about 15 solar masses per year, and that's across the whole of the panoply of stars between 0.1 and 100 solar masses. Okay. This is the low redshift equivalent, of course, is M82. And I think we'll find, if I come up here, yeah, here we go. This object here, its position, 1237.08 plus 6210.56. So that is 15 solar masses a year. It's 5 times more luminous, intrinsically luminous than M82, but M82 is about 3 solar masses per year. It's 375 times further away than M82, and the light travel time is about 4.5 gigayears. So this is an image at the time when the solar system, and the sun, the solar system were just beginning to form. Okay, that's sort of redshift of I have to look that up, but it's about 0.3, something like that, I think. Okay, AGN within starbursts. Here is Hubble Space Telescope image of these galaxies, and these are the redshifts of them. This one's at 0.4099. These are actually measured by ground-based telescopes. They don't need the full angular resolution, provided they can simply separate them, and they can actually and they have huge amounts of collecting area, more than the Hubble Space Telescope, so the redshifts are taken from the ground. So it's a steep spectrum starburst galaxy with extension along the major axis of the galaxy here, but there's also a emission associated with the nucleus in here. It's 76 microgalaxies in total. There are no interacting galaxies. This is at 0.5186 redshift. This is at 419310384. There's nothing else at the same redshift, so these are not associated, even though they might appear that these two are interacting. This one is closer and that one's further away. Okay. Radio emission from the central region is about 10 to the 11 solar mass C/2 galaxy. This has optical emission from here, so there is some nuclear emission and the extension. I say light travel time is about 5.2 gigayears here. Star formation rate is about 41 solar masses per year, but the C/2 galaxy not only has light emitting from the AGN, but it also has some X-rays from the AGN, so the AGN is present, but it doesn't seem to be contributing much of this because we have measured the size of this with eMerlin, and we resolve this and there's no compact component within it. And also, if you take telescopes across the world and look for things at milliarc second scales, they find no detection in here. So this looks like a big nuclear starburst rather than an AGN. But the AGN is there in the X-rays and in visible light. And that's not unusual. These are radio quiet AGN, and we have them in the local universe as well. And then I just want to talk to you about this one. This is quite an unusual source. This is a merging pair of galaxies and radio emission from both the two nuclei which are coalescing. And basically this is the colour HST image of it, and this is almost exactly the same as a nearby 55 million light year away pair of galaxies merging called the antennae. And you can see that's the HST image of the antennae. This is the HST image of this object, much further away but very similar. And you're getting radio emission here, HST image there, and you can see all these stars being formed by the interaction. That's what's happening also here. You can see that there's this head across the central region and this tail back in towards this tidal tail going down here. And I'll go into detail about what the VLA 10 gives, but basically the low frequencies of eMerlin and VLA and low frequencies bring up this this steep spectrum emission very strongly, and it's very difficult for the VLA to do that at higher frequencies because it just disappears. But they need to go to higher frequencies to get the same resolution because their aperture is smaller. That's why having a large aperture and low frequencies can actually map out these objects. That's the image from eMerge. That's it overlaid on the HST image, and here are the tidal tails coming out from that. Here are two interacting galaxies. These are both at the same redshift, and these two are actually merging, so this is a close group of galaxies. Star formation rate for the antennae is about 70 solar masses per year. This is massive. It's just under 1,000 solar masses a year. It's 14 times more luminous and 150 times further away. And that's the actual full HST image of the antennae. Of course, it's very close to us. And that's what we get at the distance we're talking about, but it's really fantastic what you can see there. But actually, this is 150 times further away. So, I'll not go through any more of these. I'll just come to... these are some of the AGN in here. I haven't had time to tell you much about that, I'm afraid. I'm sorry. But the AGN are showing all of these are these systems where they do not escape the galaxy, apart from this one here. This is a classical double, it's a wide-angle tail. But these are all showing that these jets are disrupted before they get out from the galaxy. So we need to investigate whether or not the black holes here have got enough mass or enough spin to actually generate the stable jets and the fast jets. And we'll be combining these data with data from across the globe to 11,000 kilometers, and that will then give you the chance to see whether these jets are one-sided on short time scales and moving relativistically, and when they stop. Anyway, I'll move on a bit and just say the DR1 validation for DR2 is now successfully done. It's a successful combination of wide field imaging with in the VLA, weighting schemes derived from combining images across heterogeneous arrays, combining combinations with large fractional bandwidths. So the fact that some of the telescopes are 25 metre, 32 metre, 76 metre, and especially with those across the world, that some of those are huge telescopes as well. Complex point spread function modelling for extended wide field imaging lying outside the primary beam of some antennas, dynamically scaling variable PSFs on offsets from the centre. We have dealt with all of that to actually combine these telescope images, or these telescope contributions to these wide field images, and a fully automated, sophisticated data editing within the e-learning calibration pipeline to dynamically remove the correlated interference from machine learning algorithms to maximise the image fidelity from 30 terabytes of data. We observe across a wide band, and none of that is protected, and all that is full of perfectly legal transmissions. And we have to try and get rid of the correlated parts of those transmissions that wreck our data. And to do that manually takes forever. And that's what we did with DR1, because we didn't have that. But now we've got machine learning algorithms that go through, and with our unaveraged data, and actually get rid of the data that has to got rid of. And that means that we then do get the highest sensitivity we possibly can. Anyway, that's coming. And then finally, to finish, I thought I would just point out that I missed today's announcement from the Event Horizon telescope team. They were going to give a press conference at 1 o'clock, but I was busy and then I missed it, didn't have a chance to look at it. I don't know if any of you looked at it. This was an announcement of image of the shadow of the black hole in our galactic centre. I don't know what they've seen, but what I do know is that back in 2017, they did the Event Horizon telescope, which works at about 1 millimetre wavelength with telescopes like ARMA and other telescopes across the world, including one on the South Pole, anywhere that's dry, because you can't do any millimetre observations in Britain because there's too much water and just eats them. But here is the actual image that they made from about 7 telescopes across the world, many of them at high altitude to get above all the clouds and the wet. And this is 50 microarc seconds across. This is 1 millimetre at 11,000 kilometres aperture. And they have made it, they had to use old radio astronomy techniques that we helped develop at Jodrell and elsewhere in Europe to actually make the image, because they couldn't make it fully coherent without having to process the image itself to make it coherent by making corrections against itself. But that's so. This 50 arc seconds across here, the actual size of the shadow is about 20 microarc seconds, which I made the calculation. This is a line. A line on the lunar surface, as viewed from the Earth, is about the size of that. So that's how much you can actually use interferometry and how high a set of spatial frequencies you can take. And of course we can go out into space at some point if we really want to, but we have done that in the past, but that's a bit more problematic. It's easier on the Earth.